Ever felt your house tremble when a truck passes or your phone buzz with a message? That's vibration, an everyday phenomenon, from the hum of a fridge to the roar of a rocket. Engineers constantly think about vibration because it can make or break the things we build. Ignore it, and small shakes can turn into big failures. Cracks, breaks, disasters. That's why vibration analysis is crucial. It's a mix of physics, math, and detective work to keep our world safe. Music is just pleasant vibration, a guitar string, a drum skin. But the wrong vibration at the wrong time, that's trouble. Engineers hunt down these shakes, measure their rhythm, and figure out how to calm them. We'll dive into the science of shake, rattle, and roll, discovering why every object has its own rhythm. We'll uncover resonance, where a small push can cause a massive wobble. By the end, you'll see the hidden forces at play in the machines and structures around you. You'll appreciate the science that keeps them safe and reliable. Let's get shaking, Et. So, what is vibration? Simply put, it's a back and forth movement around a central point. Picture a child on a swing or the cone of a speaker moving thousands of times per second. Both are vibrations. Vibration is everywhere. Washing machines, car engines, earthquakes, even buzzing bees. Some vibrations are useful, like your electric toothbrush or a phone's silent alert. We design these to help us. But unwanted vibrations, like a shaky car ride or a building swaying in the wind, are a nuisance and can cause damage. In factories, constant vibration can wear out machines and even damage buildings. That's why engineers work hard to predict, measure, and eliminate unwanted shakes. Controlled vibration is our friend. Uncontrolled vibration is wasted energy and a potential threat. Understanding the difference is key to safer, better technology. Vibration is everywhere, sometimes helpful, sometimes harmful. That's why it matters. Here's a cool concept: natural frequency. Every object, from a wine glass to a skyscraper, has a frequency it wants to vibrate at. Give it a tap, and it shakes at its own special rate. Its natural frequency. Think of a swing. No matter how hard you push, it swings at the same rhythm. Shorter swings move faster, higher frequency. Longer swings move slower, lower frequency. This favorite beat depends on the object's mass and stiffness. Engineers calculate natural frequency to make sure everyday forces, like engines or wind, don't match it. If they do, things can go wrong fast. Knowing an object's natural frequency is the first step in preventing resonance. It's a fundamental property, like color or weight, and it's crucial for safe design. Let's break down what controls natural frequency: mass and stiffness. More mass means a lower frequency. Heavy things move slower. Stiffness is the opposite. Stiffer objects vibrate faster. Picture two swings. A heavy adult moves slower than a child. A tight guitar string vibrates faster than a loose one. In the formula, mass is in the denominator. More mass, lower frequency. Stiffness is in the numerator. More stiffness, higher frequency. Engineers adjust these knobs to control vibration. If a part vibrates too much, they can make it stiffer or lighter to shift its frequency. Or if needed, add mass or make it less stiff to lower the frequency. It's a balancing act. Change one thing and you affect others, like strength or cost. This is the puzzle engineers solve to keep structures safe. Mass and stiffness, the secret recipe for vibration. Get it right and things stay steady. Get it wrong and you risk disaster. Now for the drama: resonance. This happens when an object's natural frequency matches an outside force. Like pushing a swing at just the right moment, each push adds energy, making the vibration bigger and bigger. An opera singer can shatter a glass by matching its frequency. Tiny pushes, huge result. In real life, resonance can wreck machines. A washing machine with an unbalanced load can shake violently if the spin matches its frame's frequency. In cars, if engine vibrations match a part's frequency, that part shakes uncontrollably. Resonance turns small shakes into big, destructive ones. It's a phenomenon engineers must always guard against. Catch it early, and you prevent disaster. The most famous resonance disaster? The Tacoma Narrows Bridge, Galloping Gertie. Built in 1940, it twisted and rippled even in moderate winds due to its flexible design. On November 7th, steady winds created rhythmic forces that matched the bridge's natural frequency. The bridge twisted violently, with the deck moving up and down by nearly 30 feet. After hours of this, the bridge collapsed spectacularly into the water. Miraculously, only a dog was lost. The lesson? Resonance can destroy even massive structures. The disaster changed bridge design forever. Now, engineers always account for vibration and aerodynamics. So, how do engineers stop disasters like Galloping Gertie? First, smart design. Adjust mass and stiffness to shift natural frequencies away from danger zones. Next, dampers. Devices that absorb vibration and turn it into heat. Car shock absorbers and skyscraper mass dampers are great examples. Sometimes, isolators are used, like rubber mounts under a fridge motor, to keep vibrations from spreading. In labs, entire tables float on air cushions to block building vibrations. Measurement is key. Engineers use sensors to track vibration and spot problems early. They analyze data, confirm solutions, and refine designs. It's a cycle: design, test, improve. With these tools, engineers keep our world stable and safe. Taming the shake is a never-ending job, but it's what keeps bridges standing and planes flying. To fight dangerous vibrations, engineers need precise tools. The most important? The accelerometer, a sensor that measures tiny, rapid movements. Attach it to a machine, and it records vibration data in all directions. This data is digitized and analyzed using a spectrum analyzer, which breaks it down into individual frequencies. The result, a frequency spectrum graph showing which vibrations are present and how strong they are. Peaks reveal running speeds, gear frequencies, or signs of trouble like resonance or loose parts. With these tools, engineers act like doctors for machines, performing regular checkups. If a new vibration appears or grows, it's a warning sign. Early detection means maintenance can be scheduled before breakdowns happen. This proactive approach, predictive maintenance, saves money and prevents dangerous failures. Vibration analysis turns chaos into clarity. It's how we keep machines healthy. We've explored the world of vibration, its rhythms, dangers, and the science behind the shake. Every object has a natural frequency, and understanding it is key to safe design. Resonance can turn small shakes into disasters, as Galloping Gertie proved. But engineers have the tools and knowledge to control vibration through design, dampers, isolators, and precise measurement. Their work keeps our bridges, planes, and machines running safely. Managing vibration means safer, longer-lasting technology. So next time you feel a hum or see something shake, remember, it's science at work, keeping our world steady. Thanks to engineering, we can control the shake for the good of all.